Hi, welcome to another video. So today we are going to talk about consistent hashing and how it helps scale distributed systems gracefully. The gracefully is the important bit here. So let's get started. So if you remember, we discussed sharding a couple of videos back and it involves its own challenges. Why? Because we need to understand which piece of data to put in which server. So for example, I have a table which has a few rows and each of the rows have an ID, of course, and there would be some data, let's say first name and then last name. And what I normally do, or is a common strategy, is that we take a key which can be the ID and calculate a hash of the key. So in this case, let's say it's an identity function, so hash of 1 is 1, let's say, and I want to distribute the data across 3 servers. So what do? I take the hash of the key, which is 1 in this case, 2 in this case, 3 in this case, and I take 1 modulo 3, which is the number of servers, and out of that I get a result which is 1. It can be either 0 or 1 or 2, and based on the modulo result I distribute them across the servers. So modulo 0 goes to server 0, modulo 1 goes to server 1, and modulo 2 goes to server 2. So this is a perfectly valid strategy to go with, except it has a few problems. So when does a problem arise? Especially when the servers are added or removed. So in case of shard balancing, let's say I have started with 3 servers and then later I decide that I need to move to 5 servers. So what do I do in that case? In that case, I need to make all these calculations again. So I will calculate 1% 5, which is 1, and then 2% 5, which is 2, and so on. So what generally happens is there are a lot of keys that are redistributed. So in this case, wherever there are some numbers where modulo 3 not equal to modulo 5, though all of those keys would be redistributed to new servers. And that's not really very ideal scenario, because in that case we need to move around a lot of data, and you of course know that migrating a lot of data to different servers is a very expensive process, and also the cache invalidation is required. Let's say I have cached a lot of data for faster access, so when the actual server data has changed, I have to rebuild the cache as well, and everything becomes messy, everything becomes expensive. So what is the solution? Let's take a look at that. Now enters hash ring, which is the very essential part of consistent hashing. So what does it do? Let's say I have a hash space. For example, my hashed values would be distributed from 0 to n. So in that case, we can imagine that it is a straight line, and in even distribution or even interval, we have something like 0, 1, 2, 3, so on, and n. So what does hash ring do? Let's imagine we warp it into a ring. So let's make a ring out of it, and we can put 0, 1, 2, 3, 4, etc. And then we put all the hash keys on this ring. Now how does it help us distribute the load? Well, first we need to calculate the hash of the server key. So in this case, it can be the IP of the server. Let's calculate the hash of it, and we'll put the servers on this ring. So let's say there is server 1, there is server 2, there is server 3, this is server 4. And then we also calculate the hash of the data as well. So in our previous example, each row's ID, we calculate the hash from it. So we'll also calculate hash of the data rows. So let's say I have D1 here, D2 here, D3 here, D4 here, D5 here. So the strategy is that we will start with a data point, and then we will store the data whenever we encounter the first server when we move clockwise from the data point. So in this case, if we go start clockwise from D1, we'll encounter S1. From D2, we'll encounter S2, D3 goes to S3, and D4 goes to S4. So how does it really help? So let's say later one of the server goes down. Let's say the S4 goes down. So in this case, what do? we need to move the D4 key somewhere else, right? Because S4 went down. In that case, we will move D4 to the next available server going clockwise. So in this case, D4 will rather go to S0. And you can also imagine similarly, rather than removing a server, if we decide to add a new server, so in this case, the D5, which previously used to go to D server 0, now will go to server 5. So what is the advantage of this? Clearly you can see only a fraction of the keys are affected, not the whole ring is affected, not all the hash keys are affected. You can see that D1 is still in S1, D2 in S2, D3 is S3, only a fraction of the keys are affected by it. So we don't really need to like move data across everywhere, cause a mayhem. Also, we don't need to invalidate cache everywhere. We only know when we add or remove a server, which range of keys are affected, and then we only rebalance those and take necessary actions of those. And that's a huge computational advantage over the traditional hashing. So consistent hashing looks very good in theory. We have a ring where there are a lot of servers. Let's draw it again. And there can be a lot of data points using the same hash function. But in reality, all these points, right, the servers and the data points, they might not be evenly distributed on this ring. So in that case, what happens? So let's say in our real life data, a lot of data points fall in this range. And by the consistent hashing mechanism, what will happen to all these data points? Everything will go to this server, right? So you can see, right, let's say this is the server 0, server 1, server 2, server 3, and you see server 0 has a lot more data points compared to server 1, server 2, or server 3. Server 1 only has 1, server 2 has 1, server 3 has 1, whereas server 0 has how many? 1, 2, 3, 4, 5, 6, 7. So that's a huge imbalance. So what can we do to actually circumvent this problem? Enter comes virtual nodes. So what do we do with virtual nodes? So whenever we put an entry for a server in the consistent hash ring, we just don't put a single entry, we also put multiple entries. So let's say S0, this is S00, and I put another entry here, S01, S02, S03, S04. And similarly for S1, we do something like that. We have S11, S12, S13, S14. And in this case, what are we doing? We are keeping multiple copies of the same server, hash of the same server identifier or the key on the hash ring. And then what do? We follow the same algorithm. Whenever we encounter a server node going clockwise from any data point, we store the data point in the server. But in this case, now the servers can be virtual nodes as well. So in this case, the first green point will go to this one. The next one will also go here, but this one will be rather stored in S0, this one also in S0, this will now be stored in S1, this will be stored in S1, and so on. So you can imagine whenever we add a server now, it will be more evenly distributed, the data rebalancing will be much more. So previously, whenever we used to remove a server, all the data points contained in the server would go to the server that is on the first one on clockwise direction. Now, because there are multiple copies of the same server, multiple virtual copies, then we will go to the first clockwise one again, but it can be a virtual node of a different server, and that helps us a lot with even distribution of data. So let's briefly talk about where consistent hashing shines. So it definitely shines where there is a lot of data and the data needs to be distributed across different partitions, especially in sharding like scenario. For example, in distributed caching, memcached, it uses the multiple cache servers which use consistent hashing, and memcached is used by Meta. Then Redis cluster, again similar concept, They use consistent hashing because of its advantage over redistribution of the data. Distributed databases, of course, Apache Cassandra and Amazon DynamoDB, they use consistent hashing. Content delivery networks, they map contents to specific edge servers based on the consistent hash values. It's a very, very widely used algorithm across the whole industry. So that's it for today. If you like the video, please share and subscribe, and I'll see you in the next one. Thank you.